Welcome. In this video, we're going to talk through some of the bond types practice problems, and we'll refer back to some of the notes from page 2 on bond types along the way. And I have some little screenshots of some of the notes from there. And so first we want to be able to identify the type of bonding found in each of the substances. And if you look over here at this flow chart, we can see how we can determine the bond type that's going to form between atoms. So if you combine atoms that are metallic, you're going to have metallic bonding. So if you combine one or more atoms that are metals, you can have a pure metal, like pure aluminum or pure iron, or you could have an alloy, which is a mixture of metals. For example, bronze is a mixture of copper and zinc. If you combine an atom, which is a metal, with a nonmetal, you get ionic bonding. So the metal is going to give up an electron, nonmetals are going to take electrons. That's ionic. If you have a combination of all nonmetals, it's going to be covalent bonding. That's where they're going to share electrons with each other. And you can have two types of covalent bonding. You can have molecular covalent or network covalent. Molecular covalent is the much more common type of covalent bonding we will see. For network covalent, there's really only 5 examples that you should be familiar with, and those 5 examples are summarized right here. So diamond, silicon, germanium, quartz, and silicon carbide. Any other combination of nonmetals, if it's not one of these 5 examples, we're going to assume it's molecular covalent. So if we go over here, carbon, diamond, that's one of our examples of network covalent bonding. The next two, CO2 and C6H12O6, they are combinations of nonmetals, but they're not one of those 5 examples of network covalent that we saw. So that means these must both be molecular covalent. Our next two, table salt and magnesium oxide, are both combinations of a metal and a nonmetal. So these are ionic bonding. And then these last two are just metals, so these are metallic bonding. So that's one thing you want to be able to do. I'm going to skip through writing formulas. We'll cover this in a different video. And I'm going to go down here to thinking about lattice energy and related properties such as boiling point or melting point. And so what we want to do here is we want to be able to look at the ionic charge and the radii of the ions involved in ionic bonding and use Coulomb's law to predict which of these substances will have the higher melting point. So if I scroll over here and look at lattice energy, the lattice energy is basically like the bond energy. So it's basically it's related to the attraction between the ions. The technical definition is it's the energy released when the ions come and stick together and form that bond. So you can think of it as basically like the bond strength for ionic substances. And that lattice energy, so that attraction between the ions, is going to be related to the variables we discussed in Coulomb's law. So that attractive force is going to be directly proportional to the ion charge. So as the charge of the ions increases, the attractive force will increase. And then inversely proportional to the distance. So the distance that we're talking about here, so let's write this in terms of ionic bonding. So the attractive force is going to be directly proportional to the ion charge. So the larger the charge, the larger the attractive force. And it's going to be inversely proportional to the ionic radius. And that's basically describes like the distance between the ions. So if you notice over here, if we compare like calcium oxide to lithium fluoride, calcium oxide, we've got +2, -2 charges. Lithium fluoride, you got +1, -1 charges. Notice how the lattice energy in calcium oxide is much greater than lithium fluoride. That's because the ion charges are much greater. So when you're looking at lattice energy, I'd say first look at the ion charges. That's going to have the biggest impact. And then if you have a group of substances that all have the same ion charge, like this whole column, all of these are +1, -1 ions. So they all have the same ion charges. So when you have ion charges that are the same, then you want to look at that second variable, which is the radius. And you want to use your periodic trends to predict the relative, radii of these atoms. So if you look on a periodic table, chlorine's got more shells than fluorine, iodine's even larger. And notice as the radius of these ions increases, their lattice energy decreases. And if you have a higher lattice energy, that means you're going to have more attraction between the ions. So that means it's going to take more energy to break those ions apart. So you're going to end up having a higher melting point. Okay, so over here, if we're looking at these substances, let's compare sodium chloride and potassium bromide. So I always want to look at the ion charges first. They're both +1, -1 ions. So now let's look at the ionic radius. And the way that I figure out the radius is by looking at your periodic table, thinking about periodic trends. Notice over here that sodium is in row 3, and so is chloride, whereas potassium is in row 4, and so is bromide. And we know that if something's in a lower row, it's got more shells, it's going to have a larger radius. So if I were to draw this out, sodium chloride might look like this, whereas potassium bromide might look like this. So they have the same charges, but if you look at like the distance between them, this one has potassium bromide has a greater distance, so it's going to be less attracted. So that means sodium chloride is going to have a greater attraction because it's got smaller ionic radii. So sodium chloride is going to have a higher melting point because we have, same ion charges as KBr, but we have a smaller ionic radii. Comparing these ones, sodium chloride and magnesium sulfide, sodium and chlorine are +1, -1. Magnesium sulfide, that's +2, -2. So your magnesium sulfide is going to have a higher melting point because the Mg and sulfur ions have a larger charge than the sodium and chloride ions, if you're doing a written description. And if I were to draw it out, your Mg and your S versus your sodium and your chloride, they're going to be roughly similar in size here. Sorry if this is getting messy. So we'll notice that the distinguishing factor here is that these have larger ion charges, so these ions are going to be more attracted to each other because of that stronger charge. Okay, so these ones in terms of increasing lattice energy. So let's first break them up by charge. We got the +1, -1 ones, which are KCl and rubidium bromide. And then you've got the ones with the ions of +2, -2 ions, which would be strontium oxide and then calcium oxide. If we look at radius, this one's going to have smaller radii. So these ones are going to have the larger radii within this grouping. So the ones with the larger radius are going to be less attracted. Remember, as distance increases, attraction decreases. So RBBr is going to have the smallest lattice energy. Okay. And then over here, again, let's see, the oxygen's the same. So just want to compare strontium and calcium. And strontium has a larger radius. And the reason why I can tell is it's in the row below calcium. So this strontium's in row 5, calcium's in row 4. So that means strontium's going to experience a weaker attraction. So here you go. This would be our ranking from smallest lattice energy to largest lattice energy. And then take a look at alloys down here. So with alloys, what we want to do is we want to look at these models and see if we can tell the difference between a pure substance and an alloy. And then within alloys, what's the difference between an interstitial and a substitutional alloy? So some things we might notice here is that in an alloy, it is a mixture. So you have more than one type of element there. And then the difference here in this substitutional alloy, the atoms that you add in are in similar size of the original atom, and they are going to replace an atom. That's why it's called substitutional. It's kind of like making a substitution in a soccer game or something, right? So you're going to take one atom out and replace it with another atom of the same size. An interstitial alloy, you are adding a element that has a smaller radius. So you're adding an atom with a smaller radius, and it's going to kind of go in between the other atoms there. So the when you similar size, you have a substitutional alloy. When they're different sizes, that's where you have that interstitial alloy. And one of the properties of metals is that they are typically malleable, which means that they can bend easily, which is why we have things, like copper wire that you can bend around and make different shapes. So that is a characteristic property of metals. And the reason why has to do with the fact that they those weak bonds between atoms, those electrons are all kind of moving freely everywhere, and it allows them to be flexible, and the planes of atoms can kind of move past each other and slide into new positions. So that's what allows metals to be malleable. Sometimes when we make an alloy, though, we end up with something that is rigid, which is the opposite of malleable. So it's something that does not bend very easily. And steel is an example of a useful rigid alloy. And the type of alloy that results in a more rigid substance is the interstitial alloy. And if you think about what we said, how metals typically can kind of easily slide past one each other and make a new formation, and that's why they're malleable. You could see that could still happen in the substitutional example, but in the interstitial example, you've got these kind of little atoms in between that kind of lock that lattice more into a rigid structure and doesn't allow it to bend as well. So interstitial alloys tend to be more rigid or hard. And here's another visual from our bonding notes on the alloys there. And so with this information here, we should be able to predict what type of alloy different combinations of metals would form. So if you look down here, we've got some alloys you might be familiar with, like brass. We were actually analyzing brass in our most recent lab, right? We're trying to figure out what's the percentage of copper in a sample of brass. And so if we look down here at the atomic radii, copper right here has an atomic radius of 128. That's in picometers. And then zinc has an atomic radius of 134. So those are virtually the same size. So I'm going to predict that it's going to form a substitutional alloy. Now let's go down and look at steel. Steel has iron right here, which is 126 picometers, but then it's got carbon, which is 77. That's a pretty dramatic difference. Carbon's almost half the size there. So with this combination, you're going to end up with an interstitial, did I spell that right? An interstitial alloy. So that's the kind of thing you want to be able to do here. Use atomic radii to predict which type of alloy will form. All right, and that's it for our overview of this page. Thanks for watching.